All right, we're going to get into species interactions today. This covers 1.1 of the APES curriculum. We'll talk about predation, symbiosis, and competition. So take a look. By the end of this process, we're hopefully going to be able to explain how the availability of resources influences species interactions. And we're going to do this first with predation. So predation is a species interaction in which members of one species, the predator, consumes the members of another species, the prey. And you see an example of predation here in this picture. The cheetah is the predator, and the cheetah is consuming the gazelle, which is the prey. But if you think of it a different way, the gazelle is also a predator in a way. The gazelle is a predator in that it is consuming the plants and the vegetation in the area, right? Which is called herbivory. It's a relationship between herbivores and the plants that they eat. So what would this food chain then look like, right? If we were to kind of map this out. The cheetah would be here, and we're going to draw an arrow. And the gazelle. So this arrow right there implies then that the energy from the gazelle goes to the cheetah. And just as the energy from the grasses is transferred to the gazelle. One of the things that happens though during that transfer is that it's not 100% transfer of energy. Some of that energy is going to be lost along the way in the form of heat. So let's make a prediction here, right? So think about our learning objective today. Explain how the availability of resources influences species interaction, and the amount of prey is absolutely a resource if you're a predator, right? So imagine for a moment that we had a decrease in the population of the gazelles. Predict what might happen with the population of cheetahs. Will they increase or decrease? Well, since there's a decrease in the gazelle population, there's less food for the cheetahs then. So the cheetah population is also going to decrease. But going the other direction too, think about the species interaction between the gazelle and the grasses. If we have a decrease in the predator, in this case the gazelle, there's going to be more opportunity then for the grasses to grow, and so without being eaten. So we'll have an increase of the grass population. Make sure that you understand what the arrows represent. The arrows in a food chain and a food web represent the transfer of energy. All right, I mentioned earlier that some of that energy is lost in the form of heat, and that is according to the laws of thermodynamics. This is the first law here. Energy cannot be created or destroyed, only transformed. That implies that we can have, like, let's say, fossil fuel that has a lot of potential chemical energy, or chemical potential energy rather, locked between the bonds that make each of the molecules up. And we can transform that energy into a different type as we use it, right? So we can transform that potential energy into mechanical energy as we move the parts of an engine. The second law of thermodynamics also suggests that high quality energy, like the energy found within electrical energy, or the energy found in fossil fuels, or between the bonds that make up our foods. So if high quality energy is transformed, there is always a loss of energy through the release of low quality energy in the form of infrared heat. That rate oftentimes is going to be friction. The particles that make up the molecules on these small systems within cells, they move, and as they move, they rub up against the other particles that make up the system, and that rubbing, it creates friction, which creates a little bit of heat loss. This is what heat loss diagram might look like in a different aspect, right? That doesn't have to do with food webs or ecology. Take a look. This is how we can apply the second law here. So like I said earlier, electrical energy is high quality energy that's produced by transforming the bonds in coal. This is a coal-fired power plant, and how it works is the area will burn the coal, producing quite a bit of heat so that it can boil water. And as the water boils, it produces steam, and that steam is used to turn a turbine, which is connected to a generator. So that generator is able to then transform that chemical energy into mechanical energy into electrical energy to create electrical energy. And the process, though, is pretty heat intensive, so you're going to lose quite a bit of heat to space. 65% of this process in a coal-fired power plant is going to be waste heat, 35% efficient. The electricity is then going to be transported through the electrical wires that you see here. And as those electrons move, they'll get a little resistance in the material that the wires are made out of. And that resistance is going to create a little friction, and we'll lose some of that then as heat loss. And then we'll assume that 90% efficiency here by the time it gets to the end user. These incandescent light bulbs are very inefficient. About 95% of that energy is going to be transformed to heat. If you've ever touched one of these incandescent light bulbs, they're very hot. They'll burn you. So they're pretty inefficient then in making light. But when we transform that high quality energy, a little bit's going to be lost as low quality heat. And we'll talk a little bit more about that when we get into food pyramids, food webs, and the 10% rule, which is coming up later in the unit. Symbiosis is an interaction between two different organisms that are living in close association. So it's, right, let's take a look at our essential knowledge. Symbiosis, long-term, close and long-term interaction between two species. There's different types that include mutualism, commensalism, and parasitism. So we're taking notes here. Let's get into each one of these and quickly and go through an example. Mutualism is a relationship that benefits both of the organisms. You're seeing here on the screen coral, and coral is actually made up of two different species organisms. The coral itself, and you're seeing the polyp here, but also inside, you look really carefully, there's these little green cells. These are algae that live within the polyp. There's this nice mutualistic relationship between the two organisms. The coral provides protection, but also waste products from its just metabolizing foodstuffs, right? And think about it, plants, algae, photosynthesizers need carbon dioxide that the coral is producing through its metabolizing of its food. It provides wastes like nitrates and phosphates too. These building blocks are used by the algae along with light that comes in from the sun. Through photosynthesis, we produce sugars and some of the other chemicals that the coral needs. So it's a nice symbiotic, mutualistic relationship between these two. Coral bleaching occurs when these algae here are only able to live within kind of a certain range of abiotic factors, right? Specifically temperature. And if it gets a little too hot in the ocean where there are coral, the coral polyp was going to release or eject the algae in a kind of a last chance effort to stay alive. And that process, when that happens, means then that the coral is no longer able to get the carbon dioxide, nitrates, and phosphates it needs to continue to live, and it will die. Coral bleaching, then, as a result, it's that bone white, calcium carbonate skeleton that is left behind. We talked about calcium carbonate earlier when we got into monolake. Another type of species interaction is called commensalism. This is a relationship that benefits one organism but does not affect the other. Here's two examples here. The saguaro cactus doesn't necessarily know that the owl is hanging out and using it as habitat and a place to potentially nest and mate. But the owl gets certainly a benefit of it, right? Because now it has an opportunity to nest and mate and has protection from outside. These barnacles here are crustaceans that attach themselves to surfaces within our ocean. And so this whale here doesn't necessarily even know that the barnacles are attached to it, or even care for that matter. But so it doesn't know or does it affect him whatsoever. And the barnacles, though, do get quite a bit of something, a benefit out of it, right? In that they get to travel all over the ocean and deposit their larvae anywhere they want, which is a benefit, right, if you're trying to reproduce. And the last symbiotic relationship is this species interaction where called parasitism. This is a relationship that benefits one of the organisms but harms the other. The tick right here is benefited in that it is able to suck your blood, but you're harmed though because you are could potentially get sick, or you're having your resources drawn from you in the form of your blood's being sucked. The tapeworm is a parasite that lives inside your intestines, and so it benefits quite a bit because it has protection from the outside world, in addition to getting all of those extra undigested nutrients that might still be working through your system. So that's a benefit for the parasite, but it harms you quite a bit because it's stealing your nutrients from you, and you don't want that. Let's get into competition. So competition can occur within or between species in an ecosystem. It's an interaction between organisms of same or different species in which both organisms are harmed. Competition is driven by the quest for limiting resources, right? Our resources on Earth are finite. And so because it's finite, there's only so many species or organisms, whatever you want to say, that can actually compete for and secure those. So the survival of the fittest, right? Only the fit is going to be able to be best adapted to be able to compete. So what does this look like here in practice? In the 1900s, there was a biologist named Georgi Gauss, and he was experimenting with paramecium. He had two different species, Paramecium caudatum and Paramecium aurelia. And he grew them in separate petri dishes, and he noticed that they just performed just fine, right? Looked like one kind of grew a little faster at a faster rate. I know that by looking at the slope on this line. And it also looked like the population density of one was a little bit higher than the other, right? This guy, this species looks like it's a little slow to start. It's a different species. It's using the resources differently, and there might even be size differences too, as to allow certain ones to grow in bigger populations than others. So he thought, okay, well that's interesting. Sure, they can grow just fine when they're separate. So he wondered what would happen if you put them together. And so he did, though. He put both populations together in a community, and he saw what happened. And sure enough, one out-competed the other species, so much so that the other species went extinct. And so Georgi Gauss is known for what's called the competitive exclusion principle. And so competitive exclusion is this idea that two species cannot compete for the same limiting resources and coexist at the same time. You can't have two different species using the same niche at the same time. It's not possible. So what does this look like in application here? So I've got these two different barnacles here, Thamylus and Balanus. Thamylus is able to live out of the water a little bit higher than Balanus, but Balanus is a little bit larger and able to take up a little bit more space. Balanus can't quite get out of the water at high tide as well as Balanus does. So let's take a look here. I found this little simulation online. So without competition, Thamylus, these white barnacles here, are able to live really anywhere along the rock that is submerged at least partially or at some time during the day, high tide or low tide, or even in the water. When I take a look at the data over here, this white diamond represents the mean, the average of where this species exists on this rock. So this is without competition. If we introduced competition with another species, what will happen? Take a look. Competitive exclusion. Balanus, the orange larger barnacles, they're not able to hang out exactly as high up as the white smaller ones are. they've got to be submerged a lot more, but they're a lot better at using up that rock space and the resources in the water than the white barnacles. They're better competitors. The white barnacle is being outcompeted is another kind of vocabulary term you need to be able to internalize. Outcompete, right? And take a look at what happens. So right, without any competition, the familous white barnacles are able to live anywhere on the rock. When there is competition, it's almost like they're being pushed up and away. And so what's kind of interesting is that earlier I said competitive exclusion principle says that two different species can't exist and coexist at the same time. And they're not really. I mean, think about it. Yeah, sure, there's some white barnacles throughout here, but for the most part, we're pushing that other population up and away. So even though they can't exist at the same time, they still do, right? Here's the question. If competitive exclusion suggests two species cannot use the resource, in this case the rock, as habitat at the same time, how is it the two barnacle species are coexisting on the same rock? It's an interesting question. The answer to that question is something called resource partitioning. Sometimes it's called niche partitioning. And we'll talk about it a little bit more in class in a moment.